Today we'll be doing the integral from 0 to infinity of the arctangent of qx divided by x times 1 plus x squared dx. And to start off, we will define a function. F of phi is the integral from 0 to infinity arctangent of phi x divided by x times 1 plus x squared dx, with the condition f of 0 is 0 and f of q is the integral we want. So now differentiating both sides, we have f prime of phi is the integral from 0 to infinity 1 over x times 1 plus x squared, and then the partial derivative with respect to phi of the arctangent of phi x dx. So this is equal to the integral from 0 to infinity 1 over x times 1 plus x squared times 1 over 1 plus phi squared x squared, partial derivative of phi x dx, and this derivative is equal to x, which will end up canceling this x. So we are left off with f prime of phi is the integral from 0 to infinity 1 over 1 plus x squared times 1 plus phi squared x squared dx. And from here we'll use partial fractions. So we have ax plus b over 1 plus x squared plus cx plus d divided by 1 plus phi squared x squared is equal to 1 over 1 plus x squared times 1 plus phi squared x squared. And now getting a common denominator, we have ax plus b times 1 plus phi squared x squared plus 1 plus x squared times cx plus d is equal to 1. So now expanding this, we'll have ax plus a phi squared x cubed and plus b phi squared x squared plus d plus cx cubed plus dx squared is equal to 1. And now factor out some common terms, we'll have x cubed times a phi squared plus c. Factor out the x squared terms, we'll have b phi squared plus d. Factoring out the x terms, we'll have a plus c, and the constants left over is plus b plus d is equal to 1. So for this expression to be true, a phi squared plus c must be 0, b phi squared plus d is also 0, a plus c is 0, and b plus d is equal to 1. So we have a equals negative c, but that means that negative c phi squared plus c is equal to 0. But for this expression to be true, it follows that c has to be 0. But because c is 0 and a is negative c, then that also is the case that a is also 0. Over here we'll have b is equal to 1 minus d. So we have a 1 minus d phi squared plus d is equal to 0. Phi squared minus d phi squared plus d is equal to 0. So this means that d minus d phi squared is negative phi squared. And factoring out a d, we have d times 1 minus phi squared is equal to negative phi squared. So dividing by 1 minus phi squared, we see that d is negative phi squared divided by 1 minus phi squared. But we said b is 1 minus d. So b is 1 minus negative phi squared divided by 1 minus phi squared. and these negatives will end up being a positive. So we have b is 1 plus phi squared divided by 1 minus phi squared, which is 1 minus phi squared plus phi squared divided by 1 minus phi squared, but these end up canceling. So we have b is equal to 1 over 1 minus phi squared. So these are all the constants of our partial fraction decomposition. So now picking up where we left off, we found that a is equal to 0, c is equal to 0, and b is 1 over 1 minus phi squared, and d is negative phi squared divided by 1 minus phi squared. So now plugging into our expression here, we have what we're going to have 0x plus b, so plus 1 over 1 minus phi squared divided by 1 plus x squared plus 0x plus d, but that's going to be minus phi squared divided by 1 minus phi squared all over 1 plus phi squared x squared is this integrand 1 over 1 plus x squared times 1 plus phi squared x squared. So now cleaning this up a bit, we have 1 over 1 plus x squared times 1 plus phi squared x squared. This is equal to 1 over 1 minus phi squared times 1 over 1 plus x squared, and then minus phi squared divided by 1 minus phi squared times 1 over 1 plus phi squared x squared. So now all that's left is to integrate both sides from 0 to infinity, but it's with respect to x. So integral from 0 to infinity dx, and then the integral from 0 to infinity dx. But we said this is equal to f prime of phi. So this first integral is a well-known integral. It's the arctangent of x with the limit of from 0 to infinity, but that evaluates to pi over 2. So we have f prime of phi is pi over 2 times 1 over 1 minus phi squared minus phi squared divided by 1 minus phi squared. The integral from 0 to infinity 1 over 1 plus phi squared x squared dx. And we'll focus on this secondary integral. So the integral from 0 to infinity 1 over 1 plus, we could rewrite this as phi x quantity squared dx, and just make a simple substitution. So we're going to let t equal phi x, but that means that dt equals phi dx. Solving for dx, we have dx is dt over phi, and the limits of integration do not change here, so we have the integral from 0 to infinity 1 over 1 plus t squared and times dt over phi. So we have a 1 over phi integral from 0 to infinity of 1 over 1 plus t squared dt, but that's exactly the integral we discussed previously, and that's pi over 2 times 1 over phi. So that integral is equal to that. So we have f prime of phi is pi over 2 times 1 over 1 minus phi squared minus phi squared divided by 1 minus phi squared times pi over 2 times 1 over phi. And one of these phi's end up canceling, and we could factor out a pi over 2. So we have f prime of phi is pi over 2 times 1 over 1 minus phi squared, and then minus phi divided by 1 minus phi squared is equal to pi over 2. We have a 1 minus phi divided by 1 minus phi squared, but we the denominator is exactly just a difference of squares. So we have f prime of phi is pi over 2 times 1 minus phi, and then we're going to have a 1 minus phi times 1 plus phi. But we see some cancellation here. This 1 minus phi factor ends up canceling. So we're left with f prime of phi is pi over 2 times 1 over 1 plus phi. And as I said in the beginning of the video, I said that f of 0 is 0 and f of q is the integral we want. So if we integrate from 0 to q on both sides, so we have pi over 2 times the integral from 0 to q, 1 over 1 plus phi, and then d phi. Well, this side we have the integral from 0 to q, f prime of phi d phi is just f of phi evaluated from 0 to q, but this will be exactly the integral we're looking for. So our integral is now pi over 2, and then the integral from 0 to q, 1 over 1 plus phi d phi, but that's a fairly standard integral. So we have the integral is pi over 2, and then the logarithm of 1 plus phi, and that's evaluated from 0 to q. And plugging in the endpoints, we have pi over 2, the natural log of 1 plus q. So now we could say that, therefore, the integral from 0 to infinity of the arctangent of qx divided by x times 1 plus x squared dx. This is equal to pi over 2, the natural log of q plus 1, with the condition that q plus 1 has to be greater than 0. And so that is the final result.